The final thing we're going to look at to wrap up our study on derivatives is L'Hopital's theorem. So L'Hopital's theorem is a strategy for evaluating limits that makes it really, really easy. The problem is we couldn't use it before because we didn't really know how to do our derivatives yet. So now that we know this, it makes some of those more complicated limits that we did much, much easier. So L'Hopital's theorem is based off of obtaining an indeterminate form, and we've already talked about these a little bit. There are 7 indeterminate forms, only 7. These are the only 7. So 0 over 0, infinity over infinity, negative infinity over positive infinity over negative infinity, 0 times infinity, 1 to the infinity power, and 0 to the 0 power, okay? So, doesn't guarantee that a limit exists. Now, you can apply L'Hopital's theorem to all of these indeterminate forms, but in this class, we're going to focus on 2, when you get 0 over 0, or when you get some form of infinity over infinity. So it's really those first 4 that are up there. Some combination of negatives and positives when it comes to infinities, okay? So, L'Hopital's theorem is this. We use L'Hopital's theorem when an indeterminate form occurs. The idea, and you can read through all of those requirements there, g prime of x cannot be 0 because we're going to divide by the derivative of g. For all x's in the interval, except possibly at the value itself, f and g are continuous and f and g are differentiable, except again, maybe at that particular point. So this is what L'Hopital's theorem says. L'Hopital's theorem says that if you obtain an indeterminate form, the limit as x approaches c of f of x over g of x is going to be equal to the limit as x approaches c of f prime of x over g prime of x. Notice we're not using the quotient rule here. We're not taking the derivative of f over g. We're taking the derivative of f divided by the derivative of g. 2 derivatives separately, okay? This is only going to work if the original limit is going to exist, but that's how we're going to come up with this. And this theorem can be applied multiple times. Now, the AP exam is really picky about how we do this. So here are the conditions that must be met. The first thing that we have to do is we need to show that the limit as x approaches c of f of x, just the top, is equal to 0, or perhaps plus or minus infinity. And then show that the limit as x approaches c of g of x, the denominator, is equal to 0, or plus or minus infinity. You must show those 2 limits separately. You cannot show that it is 0 over 0. You never want to write 0 over 0. If you write it down because you're just kind of doing the math and that's what you come up with, immediately cross it out. 0 over 0 is never an acceptable thing. We can't ever say that something equals 0 over 0 because that is not a number. That's an indeterminate. So just cross it out if you write it down because they will penalize you for that on the AP exam. Once we know those things, what's the conclusion that we can draw? Well, we can then show that the limit as x approaches c of f of x over g of x is going to be equal to the limit of, that equal sign doesn't belong there, f prime of x over g prime of x, okay? Now, just to summarize again, the AP exam is very, very picky about justifying the use of L'Hopital's theorem. Each problem must have 3 things. 1, you have to show that the limit of the numerator and the denominator approach 0 or infinity separately. That's the most important part here. You must show 2 limits. You cannot just use 1, okay? Then you're going to state that L'Hopital's theorem applies. Well, that's good, but you don't actually have to recall the theorem by name. You just have to make the correct conclusion. So 1 is meeting your conditions. 2 is making the conclusion that the limit of f over g is equal to the limit of f prime over g prime. You don't have to actually use the name L'Hopital anywhere. it's good, you can, but we don't have to. Then once we've done that, we can evaluate the limit. So we're going to look at just a couple of examples here, and then I'll leave the rest for you to look at yourself. So all of these are ones that we could do before, but it makes them a little bit simpler. So for example, on number 1, the only strategy we would have had to do this before is you would have to factor the difference of cubes in the numerator so that you could cancel out the x minus 2's and then have something that you can evaluate. And that's still fine to do it that way, but maybe you don't remember the difference of cubes. It is much faster to use L'Hopital's theorem as long as you set up your conditions. So I'm going to take the time to write this out very clearly on this one. The first thing that we need to show is that the limit as x approaches 2 of x cubed minus 8 equals 0, which it does because 2 cubed minus 8 would be 0. And we must show that the limit as x approaches 2 of x minus 2 equals 0, which it does. So those two statements right there meets our conditions. We got two limits, both equal to 0. So here's the conclusion that we can make then. So the limit as x approaches 2 of x cubed minus 8 over x minus 2 is equal to the limit as x approaches 2 of the derivative, which is 3x squared over 1. We've gotten rid of the part that was a problem, so now this is equal to 3x squared, which would be 3 times 2 squared, so we get 12. That is our limit, the end. So that's pretty easy to do. Now you have to be a little bit tedious about correctly setting up your conditions and your conclusion, but that's how we can apply L'Hopital's theorem, okay? Number 2 is very similar, so I'm going to leave that one for you to look at yourself. Let's look at number 3 that has some trig functions here. Okay, so for number 3, this is one before where we would have need to multiply by like 4x over 3x to get this to work using our special trig limits. Now that we have L'Hopital's theorem, we don't need to do that. Okay, so number 5 is the one you should have memorized, but if you don't, you can always apply L'Hopital's theorem to it. So again, the first thing we have to do is set up our conditions. The sign of 0 is 0, so both of these limits, even though they have a 3 and a 4, you're still doing sign of 0. Both of these limits come out to 0. Conditions met. So what is our conclusion? We can show that our original limit is equal now to the limit as x approaches 0 of, let's take the derivative. We have to use the chain rule. So this will become cosine of 3x times 3. So this is 3 cosine 3x over similarly 4 cosine 4x. Well, the cosine of 0 is 1. So now we end up with 3/4, and that is our final limit there. Okay. Number 4 is an interesting one to look at because if we look at our expression here, it's not written as f of x over g of x. So we have to first combine this into a single fraction. So we can multiply here times x over x, and we get that this is the limit as x approaches 0 from the right of 10x minus 3 over x squared. Okay, so if we want to use L'Hopital's theorem here, we would need to get either 0 and 0 or infinity and infinity or some combination of infinities there. Well, if I plug in 0 to the top, I get 0 minus 3. The limit as x approaches 0 from the right of 10x minus 3 equals negative 3. That right there tells us that L'Hopital's theorem does not apply. we've got to either get 0 over 0 or some form of infinity over infinity. This won't work. So that means that we just come back to our limit and evaluate it using the strategies that we had before. So we have 10x minus 3 over x squared. This is going to come out to negative 3 over 0. Now, again, that's a value that can't exist, so let's cross it out. But the value of the limit is always going to be a positive number on the bottom, no matter which side we approach 0 from. And on the top, if we're approaching from the right, that's going to be positive values of x minus 3. We're always going to end up with negative 3 as we approach 0 from the right. So we're going to end up with negative over a positive number. So this is going to go to this is going to go towards negative infinity, or you could say that this does not exist. We can still do the limit, we just can't use L'Hopital's theorem on this one, okay? So I'm going to leave 5 and 6 for you to look at yourself, copy those down into your notes from the PDF, and then you've got your homework to be working on, and I will see you to answer some questions the next time we're in class.